So to explain Raoult's and Henry's law, we're going to look at a solution that is made of a mixture of H2O plus ethanol, a type of alcohol. Imagine that we have some kind of container where we have liquid down here, and that liquid is some mixture of H2O. Let's just write E for ethanol. And let's say there is a lid on this container, and the whole thing is at constant pressure. So we might imagine that as these things evaporate, there are molecules of water that would be banging around the lid of the container and also the sides. And then there might be molecules of, let's say, alcohol. And alcohol, or excuse me, in this case, not just any alcohol, but ethanol might be banging around the container as well and contributing to the total pressure in that system. So if the total pressure here, let's just call it 1 atmosphere, it doesn't really matter what it is. If it's 1 atmosphere or any other value, that total pressure must be equal to the sum of the pressure of ethanol plus the pressure of water, which is right as P sub W. So the total pressure must be equal to the sum of those two things. But the total pressure is also going to be a function of how much ethanol and water we have here. If we have a lot of ethanol, if this value is very high, then that'll increase the total pressure of ethanol at the expense of water. The pressure of ethanol would go up and the partial pressure of water would go down. By the same token, if we increase the amount of water relative to ethanol, then this fellow would go up, etc. So let's take a look at the way those pressures might vary. So in this diagram, we're going to have, let's say, on the vertical axis, we'll just look at the partial pressure of ethanol. We can look at that as a function of the total pressure as a fraction, and then compare that to the mole fraction of ethanol in the system. So if we have pure water, then the amount of ethanol is 0. And then if we have pure ethanol, we could just say that the mole fraction then is 1. So over here, that is pure ethanol, and over here, we have pure H2O, pure water. Well, if we have pure water, if the amount of ethanol in the system is 0, then the partial pressure of ethanol should also be 0. And then if we have pure ethanol with no water in the system, then ethanol accounts for the entire total pressure. And so this ratio would be equal to 1. So we have two fixed points. We have a point down here, and then we have a point up here. And then we can draw a straight line relationship between those two. And that straight line relationship would imply that P sub E over P sub T is simply equal to X, the amount of ethanol. Or if we rearrange that, then the pressure of ethanol is equal to the mole fraction of ethanol multiplied by the total pressure. And this is what is referred to as Raoult's law. Now, the actual behavior of alcohol in that system, the partial pressure of ethanol that will be banging against the lid and the walls in the atmospheric part of that diagram that we showed earlier, might actually look something like this, where it increase and then maybe flatten out and then approach the dashed line up here. So let's take a look at this curve and see what it means. What it means is that if we take some fraction of ethanol down here, the actual pressure would be higher than we would predict from this equation here. So Raoult's law doesn't work. But it would seem to work over here. So we've got a region of the curve over here where this observed set of partial pressures, let's say these are the observed partial pressures here on that solid line. There, in this region there, Raoult's law would work. But over here, it's very far from working. This would be a very poor approximation of the total pressure of ethanol. Well, another way of treating this is take a look at this part of the curve here. It is a curve for sure, but we might be able to treat it as something like a straight line. And we could then write that the partial pressure divided by the total pressure is equal to the concentration of ethanol multiplied by some constant, H. right? So H here is the slope of that line, or we could rewrite that to say that the partial pressure of ethanol is equal to H times X sub E multiplied by the total partial pressure. If we let this be just 1 atmosphere, then that drops out and we end up with this equation here. And this is called Henry's law. So Henry's law, we use the letter H because that is the Henry's law constant. Henry's law is telling us that we have some deviation from this ideal one-to-one relationship that we're shown here, but we still have a linear relationship. We have this very simple relationship between partial pressure and composition, but partial pressure is not exactly composition. These things are proportional to one another, proportional related to the Henry's law constant H. That Henry's law constant H could be greater than 1, as we're showing it here, but it could also be less than 1. We might have some kind of solution where the behavior looks something like this. And again, at very high concentrations, we might still approach Raoult's law, but then at lower concentrations, we might have this kind of straight line relationship, where here the H is less than 1, over here we're showing it as being greater than 1. So H can have pretty much any value we like, so long as it's greater than 0. Otherwise, it would not have any meaning. So we have Raoult's law. That means that partial pressures are equal to their concentrations. Henry's law means that they're not equal, but they're proportional to this constant value H. So how does that relate to how we normally think of systems? We have these equations where you see these terms, RT times the natural log of the activity, where A sub I is the activity of some component I in solution. Well, activity is a way of looking at partial pressures, and we can also put fugacities in here too, where we have the fugacity of I. So same kind of diagram where we have X sub I, and then we have the activity of I, and we have the ideal case where we have just a straight line relationship. If there's no X, then the activity is 0. And if we have something that is pure I, and xi is equal to 1, then the activity is 1. If the activity is 1, the natural log is 0, and we don't care about this term. The compositional corrections disappear. But for anything in between, we might have curves that look like this or look like that. And then we could say that the activity of some substance is equal to a constant. Here we don't necessarily use H. We'll use lambda or gamma, or a little more commonly shown in textbooks. But again, we have some constant that relates the value of activity, the effective concentration of something, to the concentration, but multiplied by this constant lambda, where here the lambda is greater than 0 for the top part of the curve, or not greater than 0, greater than 1, or lambda I is less than 1 if we're on this bottom part of the curve. Things might be less active or more reactive, depending on how they are interacting with other components besides I in the solution that we are interested in. So when we talk about activities, we have ideal cases. Ideal is when the activity is equal to the mole fraction of the concentration of some component. And then we have non-ideal cases, where it's equal to the concentration when it is multiplied by some activity coefficient, lambda or gamma or delta in some other textbooks.